Okay, so here we go. Ideas for another video on a big New York project. Let's see what we've got. Penn Station rebuild. Yep, that's on the right track. JFK's multi-billion-dollar upgrade. Yeah, I can see that one really taking off. Oh, what's that? Oh, must be in the wrong folder. Ignore that. Next up, a new skyscraper. Yeah, love a New York skyscraper. Oh, hang on a minute. There it is again. Is that Long Island? Okay, I'm curious now. What is that thing?
Well, I was going to ask you guys to guess, but unless you're a nuclear physicist, then you probably won't know, because this right here is a particle accelerator in New York. And it's been there for more than a quarter of a century.
Right on the doorstep of the world's most famous city. But not anymore, because this spectacular contraption is now being shut down and replaced with something even crazier. It's not often that a science megaproject creates an international media storm, but that's exactly what happened in 2008 when the completion of the Large Hadron Collider saw news trucks from all over the world descend on Geneva for the official switch-on. Everyone was fascinated by the idea of smashing subatomic particles together in a massive underground ring to simulate what happened at the dawn of our universe.
And I mean, who didn't find that interesting at the time? Especially because of some of the more colourful theories that were going around.
It could recreate the Big Bang and we'd all get sucked into this black hole.
It is possible, although extremely unlikely that CERN could create mini black holes.
Which is the worst type of black hole, because we'll all get drawn slowly towards Switzerland.
But none of that should have been a concern, because scientists in America were already conducting similar experiments and had been for years, just on a much smaller scale. As far as we're aware, no one got imploded, vaporized, or teleported to another dimension. Or maybe that's what they wanted us to think.
Anyway, it's called the Relativistic Heavy Ion Collider, or RHIC, and it began operation in 2000 at the Brookhaven National Laboratory. It's one of 17 federally funded research institutions that operate under the US Department of Energy spread across the country. Again, it involved colliding particles together in a huge ring-shaped tunnel at almost light speed. You can clearly see that ring-shaped tunnel when you look down from above. Like the Large Hadron Collider, its purpose was to effectively recreate the conditions that occurred right after the Big Bang almost 14 billion years ago. It did this by firing two beams of ions in opposite directions around the 3.8 kilometer ring and smashing them together using over 1,000 superconducting magnets. These ions would typically be uranium nuclei or something similar, even gold, and the machine would have them collide together in one of two spots. We're referring to the gigantic detectors, named STAR and Sphenix, where all the data is collected. When the ions hit each other, they reached temperatures that were around 250,000 times higher than the core of our Sun. That's about 4 trillion degrees Celsius. It caused them to effectively melt, releasing the tiny building blocks that form protons and neutrons, as well as the glue-like substance that binds them together. They're known as quarks and gluons.
What a relativistic heavy ion collider, or we call RHIC, was trying to understand what was the state of matter just before the quarks and gluons started forming those protons and neutrons. So what was the state of the universe when these quarks and gluons were free to roam around in the available space of the universe?
Some pretty heavy stuff, I'm sure you'd agree. The reason they often use gold, which might seem unnecessarily expensive at first, is because it's actually one of the heaviest common elements. It means it's packed with protons and neutrons, which increases the chance of a collision, one that would create a quark-gluon plasma.
It's another name for the type of matter that existed at the time period Abbe was referring to, somewhere between 1/millionth and 1/trillionth of a second after the Big Bang.
That form of matter, where quarks and gluons are free to move around, was something that we had never seen before RHIC came along. So the questions for RHIC were about what is that form of matter? How does it behave? What are its properties? So that's what RHIC was doing.
Once the universe expanded and cooled, this plasma transformed to become the ordinary visible matter that makes up pretty much everything we know today. Now imagine all of that's happening inside a tunnel where particles collide at extreme temperatures, covered with a radiation shield made of sand and earth. It's the kind of place where things have to be done really carefully, and even the process of tunneling itself can be incredibly hazardous. With all the fast-paced drilling and grinding, as well as the atmosphere inside, exposure to dust, like silica, is very common. Being able to monitor dust exposure in real time and introduce control measures would certainly make me feel better about working in a tunnel. I've been in many of them in all different countries around the world, and I know just how dusty those places can be. That's where Trolex's Air X range can help. The Air XD dust monitor calculates the levels of dust in the air and the size of the particles, alerting workers if limits have been reached. The Air XS, meanwhile, can distinguish respirable crystalline silica from total dust loads. All of Trolex's freestanding transportable monitors feature a stainless steel casing with an IP66 rated enclosure, which protects the housing from water, environmental contaminants, and of course, dust. Intuitive device menus, an industrial-grade keypad, and a display with an RGB backlight make it really easy to use as well. They even have a data platform which provides both live and historic data of all the dust levels your monitor has picked up since you started with it, and it's completely free to use. So with Trolex, you can identify the extent of a hazard, keep it under control quickly and cost-effectively, and most importantly, keep your teams safe. You can click the link below or scan the QR code on screen to see how Trolex can help elevate your site safety today. So now we know what to do about dust particles, let's get back to the world of particle physics. If your brain hasn't melted like one of those ions by now, then all this talk of protons and neutrons might sound a bit familiar. It's because regular viewers of the B1M are going to recall my trip to Sweden, where I went inside a neutron research facility under construction called the European Spallation Source. Imagining something as tiny as a neutron was difficult enough, but now we're talking about the bits and pieces that exist inside those. RHIC was the first to prove how this plasma that appeared after the Big Bang behaved more like a liquid than a gas, which is what many scientists thought at the time. Then, when the much bigger Large Hadron Collider came along a few years later, it was able to build on these findings by carrying out higher energy experiments. So while CERN may have become one of the world's best-known scientific organisations thanks to the LHC, it was Brookhaven where most of the early breakthroughs were made. But it didn't all begin with the RHIC. Just south of that giant ring is a smaller one, where the world's leading particle accelerator at the time was launched in 1960.
This huge and complex machine, 1/2 mile in circumference, is housed in an earth-covered tunnel in order to shield people and sensitive equipment from the radiation present during operation.
Called the alternating gradient synchrotron, it was capable of shooting out protons at much higher energies than previously possible. In fact, AGS was so successful that 3 Nobel Prizes were awarded off the back of it, and it's still in use today. Those ions that were sent into the RHIC machine came from the synchrotron, and it also provides particle beams to NASA's Space Radiation Laboratory on the same site. As for RHIC itself, well, construction for what became that took place in the 1970s, but it was actually meant for a completely different project that actually never completed. That was called Isabel, and a decent amount of progress had been made, including excavating a tunnel before the project ran into trouble. Problems with the superconducting magnets proved to be too great, and the whole scheme was cancelled just 5 years after it started. A year later, it was suggested that the tunnel and the parts already made that were usable could be used to create another accelerator. And that would turn out to be RHIC, which began its first experiments almost 2 decades after Isabel was scrapped. For more than 25 years, particles were being smashed together while most New Yorkers didn't even realise it was there. That was until early 2026 when scientists decided they'd done all they could with RHIC and it was permanently switched off.
Today we're doing something rare in science. We are closing one of the most successful research facilities ever built by the US Department of Energy.
Basically, it had fulfilled its mission. It had created plasma, and researchers had spent years studying it. And yet, there were still questions that hadn't been addressed that only a new collider could answer. The main one being how the quarks and gluons, those ingredients that are found inside protons and neutrons, are actually structured, and what binds them together. That's what RHIC's replacement, the electron-ion collider, is going to set out to achieve. Now, unsurprisingly, based on its name, it's going to be colliding electrons with ions, the only accelerator in the world capable of doing so. Quarks and other particles are scattered off of the target nucleus and are then picked up by a new detector. That's where the results of those collisions are going to be, yes, you guessed it, detected. It allows teams to study the forces generated and uncover some of those secrets about quarks and gluons that continue to elude us, including one that follows on from the LHC's most famous discovery, the Higgs boson. That's the particle that gives all other fundamental particles, like quarks, their mass. But when they come together to form a proton, these quarks only account for a small percentage of the proton's overall mass. As for the rest...
That is where the electron-ion collider comes into picture. LHC determines and explained 2% or 5% of the mass of the universe. That gluon interaction is critical, and unless we understand that, we won't understand the remaining 95% of the mass.
It's a tricky task, which is why it goes without saying that building particle accelerators is not an easy thing to do. But much like its predecessor, EIC already has a head start. Brookhaven plans to use much of the existing infrastructure, including RHIC's giant tunnel, although they are going to need to make some big changes on the inside. Because it'll still be using ions, one of the two rings is staying where it is, while the second is being replaced with a ring that fires electrons. It'll work in a similar way to its predecessor, with ions shooting off one way and electrons going in the other direction before they collide at a specific point, which will be right here. At the EPIC detector. No, that's not just me calling it an epic detector, it's really what the BNL have named it. Just this one part of the machine is going to be bigger than an American school bus. Inside will be the 10-meter long barrel detector, as well as additional instruments that will extend 45 meters in each direction down the beamline.
I just want to stop there for a moment to appreciate something that I think you guys might have just noticed. That is a physical model of the detector that's clearly had a lot of effort put into it. There are even little figures of scientists standing around chatting about clever stuff. This guy looks like he's pondering something very important. 10 out of 10 guys, I absolutely love this. No notes.
Other additions include the electron accelerator, complete with a new source for generating those particles, built off to one site. Then you've got the buildings that are going to be needed to supply and amplify power, plus they might choose to add a second detector later on. It's just a possibility at the moment. While the RHIC had been offline for just a matter of weeks when we spoke to Abe, his team had wasted no time in getting started with the disassembly.
One of the rings of the RHIC has already been disconnected. There is no power on it, and we are systematically taking each magnet out and placing it in the storage area. So some magnets are moving from one part of the RHIC to another part of the RHIC to be useful in the future operations of the electron-ion collider. So that's the biggest activity which is going on right now.
More than 1,000 magnets used on the RHIC are going to be retained in total, along with the same ion source, meaning that the AGS won't be going into retirement itself for a little while yet. Support buildings, roads, electrical and refrigeration facilities, they're all being carried over to the EIC as well. In total, the EIC complex is going to comprise 34 buildings, covering over 34,000 square kilometers. And for those of you desperate to find out what that is in American football fields, the answer is this: approximately 6.5 of them. Add in 42 substations to that, along with 15 cooling towers, 28 chiller units, 5 miles of tunnel piping, and you've got a pretty comprehensive system to try and figure out. The new collider is expected to cost almost $3 billion, and that's on top of the $2 billion that was already invested in RHIC's infrastructure. It's not going to be a quick job either. The timeline doesn't have the machine operating until the mid-2030s. You see, while there's a lot less to do than if they were starting completely from scratch, this is still going to be one of the most complicated projects on the planet. We're talking about components that are incredibly specialised, because nothing like this exists anywhere else. And it's not really the kind of thing you want to rush. Fortunately, BNL isn't working entirely on its own here.
Currently, we have institutions from around the world forming about 1,600 to 1,800 people who are interested in coming and working with us. Yeah, and this is going to grow before we start operating. We're going to go, at least I'm guessing, 1.5 or 2 times larger by the time we start running the collider. But roughly, it is 50% US and 50% rest of the world. So it is truly an international endeavor.
Several of the partner firms are supplying it with high-tech components too. For example, these huge magnets that were once part of the advanced photon source at Argonne National Laboratory in Illinois are being repurposed for the new collider. It'll represent the next leap forward in particle physics, and even when more advanced accelerators are being built in the future, they'll likely be influenced in some way by the EIC. And this doesn't just all mean bigger, fancier toys for the scientists to play with. The upgrades being made here could lead to improved particle beams that are used to fight cancer, or to enhance the accelerators that are used to design computer chips, or to advance new forms of clean energy. If you're thinking that spending time exploring the origins of our universe isn't really a top priority given every other challenge we've got coming at us in 2026, then bear in mind that this stuff really could fundamentally change our world, and it's hard not to get inspired by that. Thanks again to Trolex for sponsoring today's video. Don't forget you can click the link below or scan the QR code on screen to see how Trolex can help elevate your site safety today. And as always guys, if you enjoyed this video and you want to get more from the definitive video channel for construction, make sure you're subscribed to the B1M.